Okay, moving on to the absolute value equation and inequality. Before you can get started on any of the three types, you need to isolate the absolute value first. So that's always your first step. Make sure that the absolute value is isolated. And notice that I've given you the same problem all three places. This is an equal, this is a less than, this is a greater than. So I'm going to run through this rather quickly and just to kind of refresh your memory on this. So as far as isolating the absolute value goes, it's just a series of inverse operations to isolate the absolute value, which is right here. So the first inverse move would be to add 3 to both sides. And then in the next step, I'm going to divide by 10. So I have x plus 5 equaling 4. And I can assume that that's going to be the same thing all the way down in this particular problem. Notice that I'm not dividing by a negative, so the inequality symbol that's presented the first time is the inequality symbol that will stay in the problem all the way through. And then here I'm going to have x plus 5, which is going to be greater than or equal to 4. So I'm going to go back up to the top and I'm going to find my two boundary points. So I'm going to set x plus 5 equal to positive 4 and then x plus 5 equal to negative 4. So my first boundary point is negative 1, my second boundary point is negative 9. For the equation, my solution just looks like two plotted points, negative 9 and negative 1. So this would be my discrete or countable solution set. I have two members, a discrete solution set with two numbers only. So this is my discrete solution set. And I would present in set notation, negative 9, comma, negative 1, close up with the braces. No shading needed because I only have two solutions, the two plotted points. Moving on down to the inequality, the boundary points are going to be the same, and I'll switch ink colors. The boundary points would be the same, and if you wanted to prove it to yourself, you would first take x plus 5 greater than or equal to positive 4, and then x plus 5 less than or equal to negative 4. But you're going to arrive at the same boundary points either way. And then to graph this, the greater than always graphs as an or. So here are my two boundary points. X is less than negative 9, x is greater than or equal to negative 1. Classic broken or graph in the world of, so this is where you have the continuous notation. So I'll talk about that before I get to the integral notation. Because I have a range of numbers on a continuous number range on the number line, as opposed to a solution set where I only have two members. Now my solution set is going to contain the numbers negative 9 up to negative infinity, soft, hard, which I will union with negative 1 to positive infinity, hard, soft. A continuous solution set as opposed to a solution set that only contains two plotted points. And then the last example, the last type, would be the and. Oh, I skipped over the and, I went straight for the or. So I went straight for the or. Let me go ahead and erase a little bit and I'll solve the and. So I skipped the and I'm going to clean up the board and I'm going to do the and version now. So the and version would have the same boundary points. It's just the way that I claim the continuous solution set for the and. So to show you what that would look like, I've got x plus 5 is less than or equal to 4. To set up the pair of inequalities, x plus 5 is less than or equal to positive 4. X plus 5 is greater than or equal to negative 4. So therefore, x is less than negative 1. X is greater than or equal to negative 9. And this is an and, less than is and, less than is and. Whenever the absolute value is isolated, the way that the symbol's facing determines whether it's an and or whether it's an or. If you had to divide by a negative number, if 10 were negative, the symbol would flip in the process of isolating the absolute value. So don't determine whether it's an and or an or until you have isolated the absolute value. And now let's graph this. This just is a classic graph, the classic and graph. Let's see, if I wanted to write this as an and inequality. I would have that, the numbers are arranged numerically, and let's see, the alligator's eating the x, alligator's eating the -1. So here, this would be my classic representation for the and inequality. Mimics the number line. I've got -9, -1, solid on both, and then I shade the number between. They're sharing the range of numbers between. These are the range of numbers that make both inequalities true at the same time. And then interval notation would be -9, -1 with hard brackets on both, because you've got the equal to and the solid points, solid boundary points. Let's do the word problem. So the absolute value word problem, and you are asked to write an absolute value equation and show all of the acceptable weights, provide the graph, and then write the absolute value equation. Actually, I should have said inequality, typo there. It's an absolute value inequality, and then show the unacceptable ranges. They should both be the absolute value inequality, and I typed equation. To read the problem, the widget, a manufacturer must make widgets that weigh 32 pounds with a tolerance level of 5 pounds each. So what that means is, if I have the ideal weight in the center is 32, but they will accept widgets that weigh 5 less than 32 or 5 more than 32. So that means that my two boundary points here on my graph, 32 minus 5 and 32 plus 5. So they're going to accept anything that falls within that range, including the weights of 27 and 37. So there's a graph to represent what's happening. Now, to write the absolute value inequality that represents this graph, X represents the weight of a single widget that you're going to compare. The ideal weight is 32 pounds. So the difference between the widget that you're measuring and the ideal acceptable weight of 32, what you're actually measuring compared to 32 must be less than or equal to 5. So that would be the way you would write the absolute value inequality to go along with this problem. And I just verbally explained what this inequality is representing. So here's your visual of what's happening. All of the acceptable weights fall within this range. And then the flip side, you're writing the absolute value inequality to show all of the unacceptable weights. So I'll switch ink colors for that. So I'm now showing all the unacceptable weights. Well, the number line looks exactly the same. 32 is still the center. My boundary points are still the same, but I'm going to note my boundary points with open circles because 27 and 37 are acceptable weights. So this is an or moment because I'm shading away from each other, shading away from each boundary point to pick up all the numbers that are greater than 37 and all of the numbers that are less than 27. So in this range, it's too light, doesn't weigh enough. And on this range, the widget would be too heavy. It would weigh too much, to just give a little bit of verbal interpretation to that. Now, the absolute value inequality that goes along with this is going to be a strict greater than. So once again, X is going to represent the single widget that I'm weighing at the moment. I'm going to compare that to the ideal weight of 32, just to take their pure difference. Their pure difference, if it's greater than 5, then I'm going to have to say that that's an unacceptable widget and would not be something I could sell, or I couldn't sell this and market it as being within the bounds of what I'm advertising. So that's your inequality, or actually that's your absolute value review for the test, equations and inequalities.